Discharging of a capacitor through resistor. Assuming that initially capacitor is fully charged and the charge on the capacitor is Q0 plus Q0 minus Q0. Hence the potential difference across its plates will be V0. V0 is equal to Q0 by C. C is the capacity of this capacitor. Now the switch is closed at t is equal to 0 seconds. When the switch is closed, let current I starts flowing in the circuit. I be the current in the circuit and Q be the charge flowing through the capacitor across the resistor R in time t. After time t seconds, the charge on the capacitor at this instant is suppose Q and the current is I. We can use Kirchhoff's voltage law. Assuming that capacitor initially has charge Q0. Hence, potential difference across its plates is V0 equal to Q0 by C. Now, the switch is closed at t is equal to 0 seconds. The charge will start flowing through this resistor. The current flowing in the circuit is I. Let at any instant of time t, the charge on capacitor is Q and the current in the circuit is I. Using Kirchhoff's voltage loop rule, using Kirchhoff's voltage law in this circuit, we'll have Q by C minus IR is equal to 0. Since as time t is increasing, Q decreases. Therefore, we can write I is equal to minus dq by dt. So Q by C minus dq by dt times of R is equal to 0. We'll try to bring all Q terms together. dq by Q is equal to minus dt by R into C. Now integrating. From initial charge Q0 to say the charge is Q. dq by Q is equal to minus 1 by RC integration 0 to t dt. We get it. Ln of Q by Q0 is equal to minus t by RC or Q is equal to Q0 e to the power minus t by RC. This is the charge on the plates of capacitor. So at t is equal to 0, this factor is equal to 1. Charge on the capacitor is Q0. As t tends to infinity, this will become 0. Charge on the plates of capacitor will become 0. Now we can also calculate current. Discharging current. I is equal to minus dq by dt. So differentiating it. Minus Q0 d by dt of e to the power minus t by RC. So I will be equal to Q0 by RC into e to the power minus t by RC. Q0 is maximum charge, that is equal to E into C. So we can also write E by R, that is maximum current. I is equal to I0 e to the power minus t by RC. Likewise, potential difference across capacitor, V is equal to V0 e to the power minus t by RC. Since V is equal to Q by C, so Q we know is Q0. Q0 by C is called V0. So we can also write Q0 e to the power minus t by RC divided by C. Q0 by C we can call V0. So V is equal to V0 e to the power minus t by RC. So this is how the current is going to vary. The potential across the capacitor is going to vary. And this is how the charge on the plates of capacitor is going to vary. So if you check it here, the charge is varying as Q is equal to Q0 e to the power minus t by RC. Current is varying as I is equal to I0 e to the power minus t by RC. Potential across the plates of capacitor is varying as V0 e to the power minus t by RC. So at t is equal to 0, the charge is Q0, current is I0, potential is V0. As the time goes on increasing, at t tends to infinity, here we'll have the tau value. At t tends to infinity, we are getting charge Q is equal to 0, current I is equal to tending to 0 and V tending to 0. So here we'll discuss about at 0.368 times of Q0 will be the time for time constant. Similarly, this is also time constant, this is also time constant. So let us discuss the results. At t is equal to 0, charge on the plates of capacitor is Q0. When we switch on, the current in the circuit will be I0. The maximum current flows in the circuit as soon as the switch is closed. At t tends to infinity, charge on the plates of capacitor becomes 0. Current will tend to 0 because there is no charge flowing in the circuit. So the current will become 0 and the charge on the plates of capacitor becomes 0. The capacitor get completely discharged. Third, RC has the dimension of time. It is called the time constant of the circuit and is represented by tau. At t is equal to tau, that is RC, we have Q is equal to Q naught e to the power minus t by tau. Now when t is equal to tau, this will be Q naught into 1 by E, that is equal to 0.368 times of Q naught. Similarly, current I is equal to I naught e to the power minus t by tau. When t is equal to tau, this can be written as I naught into 1 by E, or the current will be 0.368 times of I naught. So time constant of the circuit is defined as the time taken for the charge to decrease 0.36 times of the initial charge, or the current to decrease 0.36 times of the initial current. The time constant of the circuit is defined as the time taken for the charge to decrease 0.36 times Q naught, or current to decrease 0.36 times of I naught, where Q naught and I naught are the initial current or initial charge. Half-life of the circuit. It is the time taken to decrease charge or current in the circuit to half its initial value. So if I is equal to I naught e to the power minus t by tau, I can be written as I naught by 2. So we can cancel I naught. Half is equal to 1 by e to the power t by tau, or ln 2 is equal to t by tau. This time is called half-life t half. T half is equal to tau ln 2. This is called half-life of the circuit.